Adding YouTube HLS output to OBS. This project involved two high-impact softwares, OBS, or Open Broadcaster Software, and YouTube. OBS is a free and open-source platform that dominates the live streaming industry, allowing content creators to stream to major video hosting platforms such as YouTube, Facebook, and Twitch. I worked on a Google team to implement a new protocol over which creators can live stream to YouTube, called HLS. Before we discuss HLS, however, I will first provide background on OBS. OBS allows creators to capture video and audio directly from their devices, and then set parameters about the live stream they wish to create, such as bitrate and encoder type. Then, the user may pick a destination for their content and protocol over which they wish to stream. Adding YouTube HLS to OBS as an output option means giving the user the ability to live stream to YouTube using the HLS protocol. HLS stands for HTTP live streaming, a media streaming protocol that segments and indexes encoded MP4 video into chunks organized by a corresponding index file. The index file contains a list of possible streams encoded at different qualities. It delivers whichever quality of video is requested by the player over an HTTP content delivery network. In the context of my project, the role of AV inputs and the server is fulfilled by OBS. YouTube provides the third pane, the origin web server, while a viewer of a live stream could be considered the fourth pane, a client. Before I explain why I implemented HLS rather than another ingestion protocol, I first want to establish the project's motivation in the context of computer networks by defining a few terms. Quality, or resolution, refers to the pixel density of an image. Bandwidth refers to the amount of information that can be sent over a connection in a given amount of time. There is a natural trade-off between quality and bandwidth, since higher quality images require more bandwidth. When bandwidth is insufficient, the user may experience poor resolution or buffering. So why HLS? HLS has three main advantages that motivated my work. 1. Because HLS delivers content over HTTP networks, it offers improved security over RTMP. 2 is accessibility. Because HLS, when combined with newer encoder-decoders, can minimize buffering and improve stream quality. 3 is versatility. HLS allows viewers to receive the highest quality video on a real-time basis, depending on momentary changes in their bandwidth. Expanding on the meaning of improved data compression. When combined with newer codecs, meaning hardware or software that encode digital data streams, HLS can offer improved data compression, meaning that more information can be encoded in fewer bits. Therefore, users can stream at higher quality with no change in their bandwidth, or minimize buffering with no sacrifice in quality, given that fewer bits are being sent to encode the same data. It is clear from this discussion why HLS is an advantageous protocol for the OBS or YouTube user. So, having established a clear motivation for the project, I will now discuss its implementation. The background was written in C and C++, while the front end was written in XML. Overall, it was a 1,000+ line contribution. Although I coded the entire project, my major contributions can be summarized as 1. Adding support for HLS streaming output to YouTube. 2. Modifying and adding UI elements to make the new service more usable. And 3. Implementing multi-threading and synchronization to ensure optimal streaming. Implementing multi-threading and synchronization was fully unplanned and was the most difficult and innovative part of the project, involving challenging debugging and deep understanding of the principles of concurrency and synchronization. So why did we do it? Looking at stream statistics, we realized that nearly 10% of video frames sent as part of the live stream were skipped due to encoding lag, suggesting that something was very wrong. I had to look back at the big picture of OBS data flow illustrated here to understand what could be going wrong. The skipped frames that we were observed were due to a blocking write call from HLS to the final process, during which the encoder buffer would reach capacity and start skipping frames rather than passing them to HLS, as required. We solved this problem by implementing the producer-consumer paradigm, a famous strategy in which one thread behaves as a producer, placing objects into some sort of buffer or queue. The second thread behaves as the consumer, removing objects from the buffer whenever the buffer is non-empty. The buffer is protected by a mutex so that race conditions are avoided. We analyzed the success of applying the producer-consumer paradigm by comparing HLS to our baseline protocol, RTMP, which had 0% skipped frames. Initially, for HLS, 10% of frames were skipped due to blocking writes to the pipe. After implementing the producer-consumer paradigm, however, this number fell to 0%, successfully meeting our baseline of RTMP, HLS's main competitor. Impact. We can clearly see the internal metrics of success for the project, but what has its impact been on a broader scale, and what is its potential for impact going forward? Because OBS is free and open source, the software has become an increasingly important and accessible tool for social connection in this time of pandemic. HLS ingestion thus has huge potential for widespread use, both because of this increasing demand and because OBS has thousands of regular users and YouTube Live, millions. This project also has potential to improve the streaming experience and equitable access of these viewers, since HLS's improved data compression ensures that even viewers with lower bandwidth can stream at high quality. Lastly, this feature is already set to make tangible impact since it functions well on all major operating systems and was released in OBS's latest software update. HLS ingestion in OBS is not only impactful in terms of its potential to touch numerous users, but also because of the way in which it pushes the field of computer networks and video compression forward. Aside from the multi-threaded approach that was implemented to prevent bottlenecks, this project is innovative because it is the first protocol added to OBS that can support newer video codecs, such as VP9, AV1, and HEVC, which stands for High Efficiency Video Encoding. Next, because this work is open source, it provides a good example for how one might implement HLS ingestion to other video platforms and illustrates some of the intricacies of doing so. Finally, this project also encourages widespread use of newer codecs, helping us progress toward a future of live streaming that is more user-centered and accessible. Thank you so much.